welcome back. Today we're diving deep into the Nintendo Switch motherboard. I'm going to analyze the Nintendo Switch by breaking it down piece by piece, exposing its inner workings, also the best practices how to analyze, troubleshoot and repair a Nintendo Switch. So this is the main motherboard. This is the front side of the PCB. It's a small PCB. This PCB has 12 layers. On this small PCB is a dense population of different components. We will start with the first component. This is the USB-C connector. Here you can connect the USB cable to the power supply or the Nintendo dock. This small sticker is a water indicator. So if the motherboard is exposed to any moisture, this indicator will turn red. So then you know there is a possibility of corrosion or something that is damaged the motherboard. So this little resistor is a fuse, and if there is any major short on the motherboard, this fuse will be burned. Always check if there is continuity between the start of the resistor and the end of the resistor. This IC here is called M92T36. It's a power delivery chip. The M92 plays a crucial role in regulating the power input from the USB port, which is used for both charging the console and connecting it to the dock or any other device. It handles the negotiation and detection of power delivery profiles, meaning this IC will communicate with the power supply and it can ask for 5 volt, 9 volt or 15 volts. There are two MOSFETs here, so the power will go through these MOSFETs and it will go to the charging IC. This component here is a DC to DC converter, so it generates a power rail. I think it's 5 volt. This is a charging IC. It's called the BQ24193. And one of the functions of the BQ is its ability to provide a charging profile that is optimized for the battery that is used in the Nintendo Switch. So the battery is connected here on this battery connector. This IC has also built-in safety features to protect the battery and the console during the charging process. It provides safeguards against overvoltage, overcurrent and overtemperature conditions, helping to prevent the damage to the battery and ensuring a safe charging operation. This is the battery connector. Here you can connect the rechargeable battery. The first two pins are ground pins. The last two pins are the positive pins. And the middle pin is the data line for the temperature sensor. So in the rechargeable battery, there is a NTC resistor, a temperature resistor, and will give a certain value depending on the temperature. With these two pads, we can solder a resistor of 10K. And what it basically does, it fakes a rechargeable battery. So you can fake the Nintendo Switch that a battery is connected. And if you want to do some advanced troubleshooting or you want to monitor the current draw, you can solder a resistor here. And then you can see the current draw on your lab power supply. So this is the connector for the right speaker. This is the right Joy-Con connector. So the Joy-Con rail that is connected on the right side of your Nintendo Switch, that rail has a ribbon cable and the ribbon cable will go to this connector. So this charging IC has different input and outputs. The input power rail is called VBAT, that is the voltage of the battery that will go to this charging IC. And you can measure it at this pad. The output of this charging IC is called VSys. So the power rail is now called VSys. It's a voltage of 4.2 volt. The V-bus can be 5 volt or 50 volts. So it depends on what the power delivery chip is asking. So it can ask 5 volt, 50 volt or 9 volt. You will see that in the V-bus voltage here. The output of this code is called VSys. And VSys is needed for the different power regulators on the motherboard. There are two here and one on the back, and also some small one scattered around the motherboard. These two ICs are called MAX77621. It manages the power supply for the switch main processor, the CPU, and the GPU, and also the memory modules. So these two voltage regulators will only turn on when the eMMC that's connected on this connector is giving a good signal or data. If everything is okay with eMMC, it will turn those two voltage regulators on. This is the memory. It consists of two modules, each of 2 gigabytes. So in total we have 4 gigabytes of DRAM. This is the left speaker connector. This IC here is a TMP451. It's a digital temperature sensor commonly used in different applications. So it will monitor the temperature. This connector here is connected to the LCD. The LCD has a backlight. So the backlight has to be powered. And this is the connector that delivers the power for the backlight. This is the connector for the left Joy-Con. So on the left side of the Nintendo Switch, there's the Joy-Con rail that has also a ribbon cable, and the ribbon cable goes into this connector. This is the connector for the SD card module. And in the SD card module, you can insert a SD card to extend the memory. This connector here is the Wi-Fi antenna connector. So it has I think a black cable that goes to the antenna. This IC here is a Broadcom BCM4356. This is a IC that is responsible for the Wi-Fi and Bluetooth. It allows the switch to connect to the wireless networks and communicate with other devices through Bluetooth. And the Bluetooth connector is located in this section of the board. This section here is responsible for driving the LCD. This connector is an LCD connector, so this connects to the big ribbon cable that goes to the LCD screen. So this connector here is for the eMMC or the NAND. It's a module that you can plug into this connector. On this connector, we connect the eMMC module or NAND. And that's the memory where all the firmware and updates are stored. This is the power and the volume connector. So the first two pins are volume up and volume down. The third pin is ground pin. And the last pin is the power on pin. So when you short the last two pins, it will turn the Nintendo Switch on. Then we have the fan connector. So the cooling fan is connected through this connector. The game card and the touch panel PCB board is connected to this connector. And on the game card PCB, there's also a touch panel connector. And the touch panel ribbon cable comes from the LCD and it goes to the game card PCB. And from there, it's connected to the motherboard. This part here is the crystal oscillator. And the crystal oscillator is a timing element that provides precise and accurate clock signals. These square components are used as a data line filters. So they filter out any noise on the signal lines, because these signal lines will go through this IC. This IC is a Pi 3 USB. And this serves as a USB switch to handle USB data and power connections between different components that communicate with the switch, like the Nintendo dock. This big IC is called a Realtek ALC5639. It's an audio codec. This audio IC is responsible for converting digital audio to analog audio, and it will go to the speakers. So if we go back, the audio signal line from the left and the right speaker. So if you have audio problems, you could check this IC. This is a 3.3 volt voltage regulator, so it creates 3.3 volt. This voltage is used by the different ICs scattered around the motherboard. The input voltage of this IC is 4.2 volt. It's called VSIS and it comes from the BQ charging chip. So this charging IC will output a VSys 4.2 volts, and this voltage will go into this voltage regulator to create a 3.3 volt. Then we have the Max IC 77621. It's a Vcore regulator, so it creates different power rails. This is a important voltage rail because it generates different power rails, and it also enables the secondary voltage regulators. By the second voltage regulator, I mean these two regulators. So these regulators will only turn on if this IC sends an enable signal. And this IC is communicating with the eMMC. How exactly, I don't know. So if there are any problems with the eMMC, it will not turn these two voltage regulators on. So this is a LSM6DS3H IC. This IC will register the position of your Nintendo Switch. So this is the LCD backlight driver. The backlight driver is a circuit that provides the power and the control signals to illuminate the backlight of a liquid crystal display. So this IC is a MAX 17050. It is called a battery fuel gauge, and it is used to accurately measure the state of charge and provide information about the battery's capacity and remaining runtime. So in the top corner on your screen, you see a battery icon. When the battery is full and you see an incorrect percentage of the remaining charge, this IC could be faulty. This is a BH1603 IC. It's an ambient light sensor, and this sensor is used to measure the ambient light and color. This little IC here is a handshake Joy-Con IC, and it communicates with the left and right Joy-Con connectors. This is an important IC. This is an anti-piracy IC. I don't know exactly what it does, but it is paired to the SoC and the eMMC module. So if this IC is bad, then you have a donor motherboard. In the Nintendo Switch, we have 3 ICs that are uniquely paired together during the manufacturing process. That is the anti-piracy IC, the SoC, and the eMMC or NAND module. These 3 ICs are uniquely paired, and if one of those ICs is broken, then you cannot restore it, and then you have a donor motherboard, because we cannot reprogram or replace it with another component. The first thing that you have to do when troubleshooting a mainboard is to check if the USB-C port is okay by checking the pins. A USB port is a reversible connector, so you can put the cable in different orientations into the socket. It has 24 pins, so A1, A12 are the pins on the upper side, and B12, B1 are the pins underneath the connector. You cannot see them. The USB-C connector has 24 pins arranged in a symmetrical layout. To be sure that the connector is good, you have to check the physical layout of the connector to check if the pads are okay and if there aren't any pins that are creating a short. Then you can check for continuity between the pads of this breakout USB-C board. So every pad that you see here from A1 to A12, A1, A12 is located on the upper side of this connector. So A1 is the first connector here of the first pin, and the last pin A12 is here. It's the same here. This is the A1, here's the A1 till A12, and here's the A12. And if everything seems to be okay, and then we're going to check for continuity between the pads of this breakout USB-C port to the USB-C pins. So if we're gonna measure the different locations, if there is a continuity between them, then the port is okay when all the pins are making a good connection. So A1 is the ground pin. The ground pin, yeah, you can use the outer shell of this USB connector, but it eventually comes out at pin 1. Then we have the A2. If you see here, the A2 goes directly to the second location. A3. So A4 is the VCC, also known as the power. Goes to this pin. And it goes to this big pad. So you can measure it also here, here, or here. A5, you can measure it on this pad, but you can also measure it at the 5th pin. Then we have data plus line. You can measure it at this pad or at this location. Data minus, you can measure it at this pad and at this pin. The 8th pin goes to this pin. Pad number 8 goes to pin number 8. VCC will go to pin A9. Then we have A10. A10 goes to this pin. A11 goes to the second last pin. And then the ground connection. We have also the B5. And B5 is the pin that is underneath the USB-C connector. And if you measure it here, it has to also have continuity to this pad. The same is for this. If you cross measure this data line, data plus and data plus have to be connected. Data minus and data minus are also connected together. The same for the VCC. So the VCC are all connected together. And also the ground pads and pins. Here we have a little resistor. It's a fuse. So also measure the continuity between the resistor with the multimeter in diode mode. So if there is no continuity, please replace this fuse. On the back side of the board, these are the connections that you have to measure. So A11 is connected to this filter. A10 to this filter. A8 will go to this filter. A3 will go to this filter. And A2 will go to this filter. So measure it with the multimeter in diode mode to see if there is continuity between this pad and this pin. And if all the pins are making a connection on the back side, on the front side, then you can assume that the USB-C port is okay. And then you can proceed with troubleshooting the other components. The next step is to check the LCD connector, because the LCD connector often breaks or have pins that are making a short inside. So the LCD connector is located here. In this picture, you can see a LCD connector that is not good, because you can see it in this section of the connector. These pins are not making a good connection, or they are bent. And this is a picture of a connector that looks good. So all the pins are symmetrical and there are no bended pins or pins that are broken off. Always check the LCD connector because when there is a previous repair attempt, what you see a lot is that that people are shoving the ribbon cable into this connector, making it unusable. The next component to check is the M92T36 IC. This is a power delivery IC. And this is an IC that often goes bad. And how do you know if this IC is bad? If one of those capacitors here are shorted, then it's most likely that this IC is shorted. When you remove this IC and this cap is still shorted, then it's another IC on the backside. But for now, let's say the cap is shorted, you remove this IC and the short is gone. Then you can replace this IC with a new one. So this IC is located, I'm gonna go back. This IC is located here. Keep in mind that if this cap is shorted, then the probability is high that the SoC is shorted. And yeah, then it's game over. This IC fails a lot. What you see is that when you plug in your power supply, there's no current being drawn, or you see that there's no power negotiation, like 50 volt, then it jumps to 9 volt or 5 volt. If you don't see the change in the required voltage, then there is no negotiation going on between the IC and the power supply. And it can be that this IC is then broken. If there is a short on this cap, the short can be located at the Pi 3 USB IC that is located on the back side. So this is the Pi 3 USB IC. And it is the main purpose of this IC is to handle the USB data to the connector, USB-C connector, and the Nintendo dock. And often when this cap is shorted, this cap's also shorted. But when you remove this IC, the short is released. Then you know that the IC was defect. So replace this IC. So all the measurements in red are diode measurements. I've measured it with a multimeter in diode mode. You put the red probe to ground and the black probe on the pad. So if you have the same value or almost the same value, then you know this IC is okay. And if you see a major deviation, then you have to check if this IC is okay, or maybe that some component here is not okay. Also, when you remove this IC and the short is still present here, then it could be also that the short is on the SoC IC, because this line goes to the SoC, and then you have a not fixable board. Also measure these filters. So the continuity have to go from pad A to B in all directions, but they cannot cross. So if you have a signal going here and here, so you have continuity between those pads, then it's bad. It can only travel to one side. So A, B, A, B, A, B. The Pi 3 USB is located on the back side of the mainboard. This is the charging IC. It's called the BQ24193. And the V-bus power rail consists of 5 volt or 15 volt, goes to these pins here. The battery voltage goes to this pad and into this charging IC. And this charging IC will output V6, consists of 4.2 volt. So this is the BQ IC. So V-bus is coming into these two pins. It consists of 5 volt or 15 volt. It depends on what the M92 IC has negotiated. So if the power supply has to deliver 15 volt, you will see 15 volt here. And if the power supply is delivering 5 volt, you could see 5 volt here or 9 volt. So the BQ is a charging IC. It will charge the battery and also deliver power to the system. It is called V6 4.2 volt. So that's the output. The battery voltage goes into this IC and it will output the 4.2 volt. It's also an input. So when do you know if this IC is bad? Well, one of those caps can be shorted. So if one of those caps are shorted, replace this IC. So if this cap is still shorted, then the short could be with one of the voltage regulators that is connected to this power rail. Also measure the diode reading to see if you have any reading that is deviated from the normal readings. If you connect a USB-C cable to power up the system and you don't see any current draw, that could also be an indication that this IC is not charging the battery. So this is the BQ IC, and this is the same area. So here you can see the lines that are connected with each other. So these three caps are located here. So you can see the upper layer wiring. It's pure for reference, and that's it. This is the MAX 77620 voltage regulator. It is responsible for generating the most important voltages to the core components like Vcore, vMem and other ICs. It will also send an enable signal to the second stage voltage regulators. That is the MAX 77621. This IC is located on the back. It will send an enable signal to these two ICs to generate the 0.8 volt. These regulators will only turn on if the eMMC is okay and all power good enable signals are okay. When you power on your Nintendo Switch, there's a boot sequence, and the boot sequence is divided into two parts, the first boot and the second boot. In the first boot, there will be different power rails available, and in the second boot, there will be other power rails available. So if there is something wrong on the motherboard, or there is some software corruption in the eMMC, the second boot will not be activated, and the Nintendo Switch will not boot up. How to analyze if the first boot and second boot is successful? We will analyze that in the next few sheets. So on a healthy Nintendo Switch, when you turn the switch on, this will happen. The first boot will start. So on V6, there will be 1.05 volt present. Also the V1 will be present. So that's the 1.8 volt. V2, the 1.3 volt. V4 is 1.1 volt. V7 will be 1.05 volt. Let me see, V9, that is the 3.3 input voltage. This comes from the 3.3 voltage regulator. And then we have V10. Here's V10, and that is 1.0 volt. So in first boot, all these voltages have to be present. And when we start the second boot, the first boot V6 will be not available. So V6, the voltage on V6 will disappear. The one and second boot voltage rail will be always present. But in second boot, the V8 will power up. So that's 3.3 volt. V11, that is 2.9 volt. V12, 1.3 volt. And V13 is 1.05 volt. So when you have all the power rails that you expect, the Nintendo Switch will boot up. Also remember V5. So this V6, and that's always 4.2 volts. And this comes from the charging IC. So to recap, when the Nintendo Switch is booting up, the first boot will start. V6 will be 1.05 volt. Then these voltage rails will be powered up. And when the second boot start, the V6 will be 0 volt. And these voltage rails will be available. Please be aware that when you are measuring the power rails and the voltages are disappearing, and that's because the Nintendo Switch is going into standby mode. So then you have to press or jump the power pins again to start the sequence, and then you can measure it again. So if the voltages are disappearing, it's probably because the Nintendo Switch is going into a standby mode. The MAX 77621 voltage regulator for the second boot phase is located in this area. And this is how it looks like. So this is the max IC. The input voltage of 4.2 volt comes from the charging IC. It will serve as an input for this voltage regulator. This trace is probably the enable signal to turn this IC on for generating the 0.8 volt at the output. In red are the diode measurements. So all diode measurements in this sheet. So what you do is you put the red probe to ground and the black probe on the component that you want to measure. You put the multimeter in diode mode, and then you can compare the values of your readings with the diode readings in red. When you compare your values with the values here and you see a deviation, then it could be a problem that you should troubleshoot. So all the measurements in blue are the resistance measurements. You put your black probe to ground and the red probe to the component that you want to measure. You put your multimeter in resistance mode, and then you can compare the values with the values in the sheet. You can also check the output power rail. In this output, we expect 0.8 volt, and if there is a short or it is a different value, you should check the output with the ohm meter. Remember also when you measure the output power rail of 0.8 volt, when you measure it in diode mode, you get a short. But remember, these lines are a low resistance line, low impedance power rails, meaning the resistance is very low. So measure the output with the multimeter in resistance mode and compare the resistance with the resistance given here. If there is any short, then you can solder a wire onto this pad and inject 1 volt and to see what the amperage is of the lab power supply. And then you can check which component in the power line is getting hot. With the thermal cam, you can see which component gets hot, and then you can replace that component if you don't have a thermal camera. You can also use isopropyl alcohol. You put it on the components nearby and see which component evaporates the alcohol. So then you know what the suspect component is. So the other voltage regulator is located here, nearby the Wi-Fi IC. This is how it looks like. And eventually this is an exact copy of the previous one. So this is also the same voltage regulator, but at the first location. This is the same voltage regulator, but at the second location. And all the components here are mirrored. So it's almost the same, but it's a different layout. So we have here the input power rail, the VSys 4.2 volt, comes from the charging IC. We have the output that is 0.8 volt. And if you measure the diode readings or the resistance measurements and you have a deviation, then you have an indication where to troubleshoot. Also important to know is this voltage regulator and this one will only turn on when there is no shorts on the motherboard or the eMMC is not a defect. So if there is no software corruption at the eMMC or the eMMC itself is working okay, then these voltage regulators will turn on. If there is a problem with eMMC or some other component for generating some voltages, these voltage regulators will not turn on. So when your Nintendo Switch is stuck at first boot, then you can see that these regulators will also not be activated. The 3.3 voltage regulator is located on the back. So this is the area where the 3.3 is created. This is how it looks like. So this is the EN chip. This is the voltage regulator that creates the 3.3 volt. So this is the output power rail. This is the input, and the input comes from VSys. It comes from the charging IC. So if this voltage is missing or shorted, then Nintendo Switch will not boot up because we have a missing power rail. So if there is a short on the 3.3 power rail, you can solder a wire here and inject 1 volt. And then you can check with your lab power supply what the current draw is. And if it draws like 1 amp, then you can check which component gets hot and replace that component. The LCD driver for driving the LCD screen is located nearby the LCD connector. So this is the area. This is how the area looks like. The LCD driver is responsible for controlling the display on the console screen. And you can check all the nearby components and compare the diode readings with the readings that you have. And if you see a deviation, then you can analyze the component. Most of the time, this IC will be faulty and the components around them are usually okay. But always check the surrounding components. The audio IC is located on the backside of the PCB board. It's in this area. It's a Realtek audio IC. If you have any audio problems, you can check this IC with these diode readings. If you have any audio problems, like no sound, you could check this area. Check all the capacitors on shorts. And if there aren't any shorts, you could check the diode readings. So if there is a reading off, then you can change this IC. Next, we're going to analyze the charging circuit. To do that, we have to connect the battery. We have to connect a USB-C meter. We connect the power supply. If the charging voltage is 15 volt, this means that the power delivery request to this M92 IC is working. So we can assume that this IC is okay. Here you can see the charging current. When this battery is full, then the charging current goes down. And when this battery is empty, then the charging current will be very low. And after a while, the charging current will go up to 1 amp. So if you see that, then it's okay. Let's say you have 0 current draw, then most of the time the M92 is faulty, but it can also be the BQ charging IC. And also check the Pi 3 USB IC on the back. Check for short near the ICs. And if you find a short, replace the component or the IC. Another way to check if the charging circuit is okay, you can attach a multimeter with the black probe to the ground and the positive lead to the red wire. The voltage that you see on your multimeter in voltage mode, write the voltage down that is measured between those two terminals. And at 10 minutes, measure the voltage again. And if it's correct, the voltage should be higher than the previous measurement. That is how you can confirm that the charging circuit is okay. If you measure the voltage and the voltage goes down, then there could be a short somewhere on the board, most likely in the charging circuit. So then you have to find the short that is responsible for this symptom. When you turn the Nintendo Switch on, Nintendo Switch will start a boot sequence. And to check if the boot sequence is okay, it's divided into 2 parts. We have the first stage boot and the second stage boot. In the first stage boot, we're gonna check the current draw in a situation that there's no battery connected. First, check that on the VSys power rail there is no short, so measure it with a multimeter in resistance mode. And if there is no short, we can proceed. Solder a red wire to the coil. Solder a black wire to the ground. Set the lab power supply to 4.2 volts and connect the leads to the lab power supply. Because we have no battery connected and we did not shorted the power button, the current draw of the lab power supply should be between 1 and 5 milliamps. When we short the power button, so we want to turn the switch on. Because there is no battery connected, it will go to first stage boot, but it will not proceed to the second stage boot. When we short the leads of the power button, the lab power supply will jump to plus minus 200 milliamps. When you see this happening, then you can confirm that the first stage boot is okay. When you don't see a current draw, or you see a higher current draw, there could be a short somewhere on the board. So then you have to troubleshoot it with the multimeter to try to find out why the current is different from the 200 milliamps. So if the current draw is 200 milliamps, it's okay. And if you have a deviation in the current, then you have to troubleshoot further. In the second stage boot, we're gonna fake the Nintendo Switch in believing that there is a battery connected with 100% of charge. When we short the power button pins, we hope to see that the Nintendo Switch starts the first stage boot and the second stage boot, because if the second stage boot is successful, then the Nintendo Switch will turn on, you will see the logo on the screen, etc. So to do that, remove the battery. We're gonna solder a red wire to the feedback power rail. This voltage battery will go into this charging IC. It will output the 4.2 volt to this coil. And that's the VSys power rail then. From there it will go to the other ICs. We will solder the black wire to ground. We will connect the feedback power rail to the lab power supply, and we set it to 4.2 volts. Next, we have to solder a resistor of 10K between those two pads. Set the power supply to 4.2 volts. So next we have to jump the power connector to start the boot sequence. So in the first stage boot, we should see a plus minus of 200 milliamps. It's the same as that we discussed in the previous sheet. So we have to see here a 200 milliamps current draw. And second, then we have to see that the current draw jumps to 400 milliamps. And if it does jumps to 400 milliamps, that's a good sign. When it doesn't jump to 400 milliamps, there could be a problem. When there is no second stage boot, the following could be wrong. So the Vcore voltage regulators are missing a power rail. The second stage power regulators are not creating the power rails that is needed. Maybe there are some shorts near them, or maybe the IC is defect. Also, the eMMC module that's connected here could be defect, or there can be a software corruption. Also, the RAM could be defect, because in the second stage boot we are powering from the feedback power rail. So the Pi 3 USB that's on the back and the M92 are not important in this process. So if there is something wrong with those two IC, it shouldn't stop the booting process. So when you have a current draw of 400 milliamps, so that's a very good sign. So you have a bootable switch. Don't be surprised that the current will go back to sleep mode. So let's say between the 1 and 8 milliamps. That is because after a while the switch will put itself in standby mode. So if you eventually see that the current draw goes back to almost zero, that's okay. When we know the current draw in the first stage boot and second stage boot, we can make a assumption or analysis. If in the first stage boot you have a maximum current draw, you probably have a short somewhere on the motherboard. In a working situation, the first stage boot will draw plus minus 200 milliamps, and then it will jump to 400 or 500 milliamps, and after a while it will go to sleep, and then you see that the current draw will drop back to 8 milliamps. This is the healthy full stage boot. You can also have a successful full stage boot, but you don't see anything on the screen. So probably the LCD or the backlight driver is defect. So you have to check those components. So when you have 200 milliamps in the first stage boot and nothing else happens, you probably have a eMMC problem. The chance that it is eMMC is 60% in my case. When you see a current draw of 100 milliamps in the first stage boot and nothing else happens, the max IC 77621 could be defect, so check that circuit. When you see 200 milliamps in the first stage boot and in the second stage boot it goes from 300 to 700 milliamps and then back again to 300 and 700 milliamps and eventually it jumps back to 200 milliamps, that could be a sign that the M92 IC is defect. So you have to check that circuit. There is another way to test if the problem is with the eMMC module, or maybe there is some short somewhere on the motherboard that you can't find. RCM is a specific mode that allows users to load custom software or perform low-level operations on the device. RCM is often accessed by connecting the device to a computer with a USB cable and using specialized software tools to communicate with the device. So in this case, we are using the Tegra RCM software to diagnose the problem. So what you have to do is you have to connect the battery, you have to connect the LCD, you have to connect the backlight, and then you have to download the Tegra RCM software. You have to install it on your computer. And then you have to start the application. Next is to connect the USB-C to your computer. If you start the program, you get this window. And when you connect it to the Nintendo Switch motherboard, one of this picture will be shown. So when you connect USB cable and you get this picture, that means your Nintendo Switch is in a recovery mode. When you get a red picture, it's not in recovery mode. So when you get the green picture, this means that the Nintendo Switch is in a recovery mode because it can't read the eMMC. So the possible cause could be a corrupted or broken eMMC or a bad M92 IC. So when you get the green icon, most probably is the eMMC, but it could also be this IC. When you get a red icon, this means there can be a short somewhere on the board or a component is bad. So you could check the M92 chip, the BQ chip, the Pi 3 USB IC. Also, you can check the voltage regulator, but it's probably not the eMMC that's faulty. So this is another way to check in which direction you can troubleshoot. This is the famous blue screen of death, and the causes are very simple most of the cases. It can be three components. First one, it could be the APU or the SoC. It could also be the RAM modules and the eMMC module. Most of the cases, a bent motherboard is the root cause of the blue screen of death. And that is because the solder balls beneath these ICs are broken, or you have ripped pads. And the fix is simple, but it requires very good rework skills. To fix a blue screen of death, what you have to do is you have to remove the ICs, reball them, and reflow them back into position. But before doing that, it's important to check which IC is the cause. To find out which IC is the cause of the blue screen of death, what you can do is you can press with your finger on the IC, and when you turn the console on and you see the Nintendo boot logo, then you know which IC is the problem. So for the APU, try to press in every corner and try to power on the console. And if you see the logo, then you know the APU is faulty. Well, the solder balls are broken. When you press on one of the RAM module and it turns on with a Nintendo logo, then you know that you have to reflow or rework the NAND ICs. And sometimes also can be the cause that the eMMC has bad solder joints. So by reflowing, reballing, you can solve this problem. Here you can see the traces between the APU and the RAM. So the blue screen of that is 99% a data problem. So the data from the APU cannot communicate with the RAM or the eMMC. That's because beneath the ICs there are some ripped pads or maybe broken solder balls. and most of the times it will be located on the outer side of the ICs, so most likely on the border side. And as you can see, there are lots of signal lines going from the APU to the SoC. And when a user bends his Nintendo Switch by sitting on it or throwing it, those balls can be broken, and also the pads could be ripped. This is the orange screen of that, and you can get this orange screen when the Wi-Fi or Bluetooth IC is broken or defect. So that is this IC. When this IC doesn't work correctly, you will get a orange screen of that. What you can do is you can replace this IC, but before doing that, you can try a reflow first. And if that is not successful, you can replace this IC. When you don't get an orange screen of that, but the Nintendo Switch is working fine, but only you cannot connect to Bluetooth or to a Wi-Fi network, then it's also 99% chance that this IC is faulty. You can see the traces that goes from the Wi-Fi IC. Most of the data lines will go directly to the APU. So when you have Wi-Fi problems, Bluetooth problems, it's most likely that this is the cause and not your APU. If the touchscreen of the Nintendo Switch is not working or not working correctly, be aware that you have to get the right version of the touchscreen for your Nintendo Switch. So if you have a version 1 Nintendo Switch, probably you have a version 1 game card reader, then you need a version 1 touchscreen. When you have a version 2 Nintendo Switch, then you have a version 2 game card reader, then you need a version 2 touchscreen. The difference is a version 2 has a QR code here, and a version 1 has a number printed on the ribbon cable. So please check the old touchscreen. If it is a version 1 or a version 2, then you can get the correct replacement part of it. This is the Joy-Con connector nearby the battery. And in red are the diode measurements. In blue are the resistance measurements. So you can compare it. And if you see a deviation, then you can troubleshoot into that specific component. Same as here. This is the left Joy-Con connector. And this is the backlight connector for the LCD. This is the SD card connector with all the correct values. So this is the connector for the LCD. Compare it with your own readings, and if you find a different value, then you can focus into that problem area. Because this LCD connector gets a lot of damage because of a previous repair attempt. So always check the physical layout of the connector and measure all the pins. This is the eMMC connector on the motherboard. This is the eMMC connector on the module. This is where the eMMC is located. This is the fan connector and the power volume up, volume down. This is the connector of the game card module. These are the values. So this was the last chapter on repairing Nintendo Switches. I hope you enjoyed the content and found it informative. Thanks again for watching, and we will see you in the next video. Thank you. Bye bye.